Welcome to the lecture on Artificial Intelligence in Corporation and Forecasting. This is your Professor T. Fareed Muhammad. We will take our running use case of stock market forecasting. This is a broad topic. We will look at one aspect of this forecasting, and that is time series. So what is time series? Here are a few examples of time series data like stock prices, sales data, weather data. Let's look into this in a little more depth. Time series data is a sequence of data points collected or recorded at constant time intervals. It is widely used in various fields such as finance, economics, and meteorology to analyze and predict trends over time. One common application of time series data is in the analysis of stock prices. For example, consider the daily closing prices of a company's stock over a year. This data can be plotted on a graph with time on the x-axis and stock price on the y-axis. By examining the trend, seasonality, and volatility in the data, investors can make informed decisions about buying or selling stocks. They can identify patterns such as upward or downward trends, cyclical movements, and sudden spikes or drops in prices, which can be crucial for predicting future stock performance. Another important application in time series data is in sales data analysis. Retails and businesses use time series data to track their sales performance over time. For instance, a retail store might record its daily sales figure for a year. This data can help the store identify peak sales periods such as holidays or special promotions and understand how external factors like economic conditions or marketing campaigns affect sales. By analyzing the time series data, the store can forecast future sales, optimize inventory management, and plan effective marketing strategies to maximize revenue. This predictive analysis allows businesses to stay competitive and respond proactively to market changes. Weather data is another example where time series analysis is extensively used. Meteorologists collect data on various weather parameters such as temperature, precipitation, and wind speed at regular intervals. For example, daily temperature readings for a city over a decade can be analyzed to understand long-term climate trends. This data can reveal seasonal patterns such as a hot summer or a cold winter going to be, as well as anomalies like heat waves or cold snaps. By studying these time series data, meteorologists can make accurate weather forecasts, issuing timely warnings for extreme weather events, and contribute to climate research. This information is vital for various sectors, including agriculture, tourism, and public safety, as it helps in planning and preparedness. Time series data is a powerful tool for understanding and predicting trends in various fields, whether it is analyzing stock prices or making investment decisions, tracking sales data to optimize business strategies, or studying weather data to forecast climate patterns. Time series analysis provides valuable insights by identifying trends, seasonality, and anomalies in the data. Individuals and organizations can make informed decisions to prepare for future events effectively. Let's look into stationary time series in a little bit more depth. A stationary time series is a type of time series data where the statistical properties such as mean, variance, and autocorrelation remain constant over time. The stability makes it easier to analyze and predict future values. One key characteristic of a stationary time series is a constant mean. For example, consider the daily average temperature in a city with a stable climate. If the mean temperature remains relatively constant throughout the year, the time series is set to have a constant mean. The consistency allows for more accurate forecasting as the average value does not fluctuate significantly over time. Another important property of a stationary time series is constant variance. Variance means the spread of or dispersion of the data points around the mean. In a stationary time series, the variance should not change over time. For instance, if we are analyzing the daily sales of a product that has consistent demand, the variance in sales figures should remain stable. This means that the fluctuations in sales are consistent and do not exhibit increasing or decreasing volatility over time. Constant variance is crucial for reliable forecasting as it ensures that the predictive models can accurately capture the underlying patterns of the data. Autocorrelation is the third key property of a stationary time series. Autocorrelation measures the correlation of a time series with its own past and future values. In a stationary time series, the autocorrelation structure should remain constant over time. For example, consider the monthly unemployment rate in a country with a stable economy. If the unemployment rate exhibits a consistent pattern of correlation with its past values, the time series is said to have constant autocorrelation structure. This consistency allows economists to make accurate predictions about future unemployment rates based on past data. By ensuring that the mean variance and autocorrelation remain constant, a stationary time series provides a robust foundation for time series analysis and forecasting. Why stationary matters in forecasting? How non-stationary data can lead to inaccurate forecasts, and the benefits of using stationary time series for stock market forecasting. Let's look into this in a little bit more depth. Non-stationary data in the stock market can significantly impact the accuracy of forecasts, leading to unreliable and potentially misleading results. One of the primary issues with non-stationary data is that it violates the fundamental assumptions of many traditional econometric models, or in other words, econometric models. These models often assume that the statistical properties of the data, such as mean, variance, and autocorrelation, remain constant over time. When these properties fluctuate, as they do in non-stationary data, the models can produce spurious results, indicating relationships between variables that do not actually exist. This can lead to inaccurate reasoning about the relationships between different time series, making it impossible to draw accurate conclusions. Another critical aspect is that non-stationary data is inherently unpredictable. Financial time series, such as stock prices, often exhibit trends, seasonal variations, and other forms of non-stationarity. These characteristics make it challenging to model and forecast future values accurately. For instance, if the mean and the variance of stock prices change over time, historical data becomes less reliable for predicting future movements. This unpredictability can result in poor understanding and forecasting, as the models struggle to capture the dynamic nature of the data. To address this, financial analysts often transform non-stationary data into stationary form. Techniques such as differencing, detrending, and seasonal adjustments are commonly used to stabilize time series data. Differencing, for example, involves subtracting the previous observation from the current observation to remove trends and make the data more stationary. These transformations are essential for improving the reliability of financial models and producing more accurate forecasts. Techniques to achieve stationarity. Let's look into differencing, log transformation, and detrending in the arena of artificial intelligence with an example. Differencing, log transformation, and detrending are common methods used to achieve stationarity in time series data. The integration of artificial intelligence can enhance these techniques. Differencing involves computing the differences between consecutive observations to stabilize the mean of the time series. The method is particularly effective for removing trends and seasonality, making the data more stationary. For instance, if a stock price series exhibits a trend, differencing can help eliminate this trend, resulting in a more constant mean. Artificial intelligence can automate the process of determining the optimal differencing order by analyzing an autocorrelation function or ACF implementation and partial autocorrelation function or PACF plots, ensuring that the transformed series is stationary. Log transformation is another technique used to stabilize the variance of the time series, especially when the data exhibits exponential growth. By applying the logarithmic transformation, the variance becomes more constant, which is a key characteristic of stationary data. For example, GDP data often show exponential growth, and taking the logarithm or log can help stabilize the variance, making the data more suitable for analysis. AI can assist in identifying the needs for log transformation by detecting patterns of exponential growth in the data and automatically applying the transformation when necessary. This integration of AI ensures that the data is appropriately transformed, enhancing the accuracy of subsequent analysis. Testing for stationarity. Statistical tests for stationarity, such as augmented Dickey-Fuller test. How to interpret the results of these tests? Let's look into that with an example. The augmented Dickey-Fuller or ADF test is a statistical method used to determine whether the time series is stationary, which is crucial for accurate forecasting and analysis. The ADF test is an augmented version of Dickey-Fuller test designed to handle more complex time series models by including additional lagged terms to account for higher order autoregressive processes. The test values and also it evaluates the null hypothesis that a unit root is present in the time series, indicating non-stationarity. If the null hypothesis is rejected, the test series is considered stationary or trend stationary. Interpreting the results of the ADF test involves examining the test statistics and the p-value. The test statistic is a negative number and its magnitude indicates the confidence level of a unit root's presence. A more negative test statistic suggests stronger evidence against the null hypothesis, implying that the time series is likely stationary. The p-value provides the probability of observing the test statistic under the null hypothesis. A low p-value or probability value, typically below 0.05, indicates strong evidence against the null hypothesis, suggesting the time series is stationary. Conversely, a high p-value or probability value fails to reject the null hypothesis, indicating the time series is non-stationary. Building forecast models, ARIMA, SARIMA, and PROFIT. Let's look into that with one example. The ARIMA or autoregressive integrated moving average model is a widely used statistical method for time series forecasting that combines autoregression, differencing, and moving averages. ARIMA is particularly effective for capturing trends, seasonality, and other patterns in the time series data. Integrating artificial intelligence with ARIMA can significantly enhance its capabilities. AI algorithms can automate the selection of optimal parameters for the ARIMA model, ensuring that the model accurately captures the underlying patterns in the data. Additionally, artificial intelligence can handle large datasets and identify complex relationships that may not be apparent through traditional statistical methods. By leveraging machine learning techniques, AI can continuously improve the ARIMA model's accuracy by learning from new data and adapting to changing trends. This integration of AI with ARIMA provides more robust and accurate forecasts, making it a powerful tool for time series analysis in various fields, including finance, economics, and the weather predictions. The SARIMA, or Seasonal Autoregressive Integrated Moving Average Model, extends the ARIMA model by incorporating seasonality, making it suitable for time series data with recurring patterns. Integrating artificial intelligence with SARIMA enhances its ability to capture both seasonal and non seasonal components accurately. AI algorithms can automate the selection of optimal parameters and seasonal parameters for SARIMA model, ensuring that the model effectively captures both short-term and long-term patterns in the data. Additionally, AI can handle large data sets and identify complex seasonal patterns that may not be apparent through traditional statistical methods. Prophet is a powerful forecasting tool developed by Facebook that excels in handling time series data with strong seasonal effects and multiple seasonality periods. Integrating artificial intelligence with Prophet enhances its ability to automatically detect and model seasonality, trends, and holiday effects, making it highly effective for achieving stationarity in time series data. AI algorithms can optimize and incorporate hyperparameters of the Prophet model, such as change point, prior scale, and seasonality prior scale, to better capture the underlying patterns in the data. Additionally, artificial intelligence can handle large datasets, as mentioned earlier, and identify complex seasonal patterns that may not be apparent through traditional statistical methods, as I discussed earlier. By leveraging machine learning techniques, AI can continuously improve Prophet models' accuracy by learning from the new data and adapting to the changing seasonal trends. Evaluating and improving the forecasts, we'll look into MAE and RMSE in a little bit more detail. Mean absolute error, or MAE, is a crucial metric for evaluating and improving forecasting models. And integrating artificial intelligence can significantly enhance this process. MAE, or mean absolute error, measures the average magnitude of errors between predicted and actual values, providing a straightforward assessment of forecast accuracy. AI can automate the evaluation process by continuously monitoring the MAE of forecasting models and identifying patterns or anomalies that contribute to higher error rates. By leveraging machine learning algorithms, AI can optimize model parameters and select the most appropriate forecasting techniques to minimize MAE. Additionally, artificial intelligence can handle large datasets and incorporate external factors, as mentioned earlier. The integration of AI with MAE evaluation enhances the reliability and precision of forecasting methods, making it a valuable tool in various applications, including demand forecasting, financial planning, and operational management as well. RMSE is also known as root mean square error. It is a crucial metric for evaluating and improving forecasting models, and integrating AI can significantly enhance this process. RMSE measures the standard deviation of the residuals, which are the differences between predicted and actual values. Providing a comprehensive assessment of forecast accuracy, AI can automate the evaluation process by continuously monitoring the RMSE, or root mean square error, of forecasting models and identifying patterns or anomalies that contribute to higher error rates. By leveraging machine learning algorithms, AI can optimize model parameters and select the most appropriate forecasting techniques to minimize RMSE. Artificial intelligence can handle large datasets, as mentioned earlier, to help us speed up the process. The integration of artificial intelligence with RMSE evaluation enhances the reliability and precision of forecasting models. Cyclical time series. Let's look into this with a little different example this time. Cyclical trends in time series data refers to long-term fluctuations that occur over irregular intervals, typically lasting several years. These trends are often influenced by broader economic, social, or environmental factors and can significantly impact various aspects of a university system. This is going to be our next example at this moment. For instance, enrollment patterns in higher education may exhibit cyclical trends due to demographic shifts, changes in government policies, or economic conditions. During economic downturns, enrollments might increase as individuals seek to enhance their skills and qualifications, while during economic booms, enrollment might decrease as more job opportunities become available. Integrating artificial intelligence into the university system or student management system can help identify and predict these cyclical trends by analyzing historical data, economic indicators, and demographic trends. AI algorithms can detect patterns and correlations that are not immediately apparent, enabling universities to make informed decisions about resource allocation, curriculum development, and strategic planning. By anticipating cyclical trends, universities can better prepare for fluctuations in enrollment, optimize their budgets, and ensure that they are well equipped to meet the changing needs of their students and faculty. Whereas seasonal patterns, on the other hand, are regular and predictable changes that occur within a year or at consistent intervals. These patterns are often influenced by the academic calendar, holidays, and other recurring events. For example, universities typically experience peaks in the enrollment during the fall semester and lower enrollment during the summer sessions. Seasonal patterns can also be observed in the demand for campus services, such as housing, dining, and library resources, which fluctuate based on the academic schedule. In contrast, cyclical trends are less predictable and more influenced by external factors that operate over longer periods. Understanding the difference between cyclical and seasonal patterns is crucial for effective planning and management within any given system. It can be university system. While seasonal patterns allow for short-term adjustments and resource planning, recognizing cyclical trends enable long-term strategic decisions that can help the universities adapt to broader changes in the educational landscape. By leveraging artificial intelligence to analyze both seasonal and cyclical trends, universities can develop comprehensive strategies that ensure their sustainability and growth in an ever-changing environment. So that's the start of learning in terms of seasonality or cyclical trends. Characteristics in the cyclical time series are repeating patterns, varying lengths, as just discussed in the university system. Identifying cyclical patterns, as mentioned earlier, the methods to identify cyclical patterns in time series are spectral analysis of the data, autocorrelation plots, and Fourier transform. I suggest you to look at these three: spectral analysis, autocorrelation plots, and Fourier transform to learn more using the library system of your university or your educational institution. Decomposing time series. Techniques for decomposing time series into trend, seasonal, cyclical, and residual components. As mentioned within the university system, we have just looked at the trends, whether they were seasonal or cyclical. However, there are residual components that we can look into a little bit more depth with an example. The residual component in time series analysis represents the variations in the data that cannot be explained by the trend, seasonal or cyclical components. These residual are the differences between the observed values and the values predicted by the model, capturing random fluctuations and noise. In a university system, residual might arise from unexpected events such as sudden changes in student preferences, unforeseen policy changes, or external shock like natural disasters. Artificial intelligence can significantly enhance the analysis and management of residual components by employing advanced machine learning techniques to identify and model these random variations. AI algorithms can detect anomalies and outliers in the data, providing insights into the sources of unexplained variability. By continuously monitoring and analyzing residuals, AI can help universities refine their predictive models, improve resource allocation, and respond more effectively to unexpected events. For example, artificial intelligence can identify patterns in student dropout rates and are not captured, and technically these are not captured by traditional models, permitting universities to implement targeted interventions and support services. Additionally, AI can integrate real time data to dynamically update predictions, ensuring that the university system remains adaptable and resilient in the face of uncertainty. Modeling cyclical time series, as discussed earlier, SARIMA, we have gone in quite depth in SARIMA. Exponential smoothing is something that we'll look into, and profit we have already discussed. So let's look into a little example on exponential smoothing incorporating artificial intelligence. Exponential smoothing is a time series forecasting method that assigns exponentially decreasing weights to past observations, giving more importance to recent data points. In a university system, exponential smoothing can be used to forecast enrollment numbers, resource demands, and other critical metrics by leveraging historical data to make informed predictions. Integrating artificial intelligence with exponential smoothing can significantly enhance its effectiveness by automating the selection of optimal smoothing parameters and adapting to changing trends in real time. AI algorithms can analyze large datasets, identify patterns, and adjust the smoothing factors dynamically to improve forecast accuracy. For example, artificial intelligence can help universities predict fluctuations in course enrollments based on recent trends in the industry, permitting the better allocation of faculty and classroom resources. Additionally, artificial intelligence can incorporate external factors such as economic indicators or demographic changes to refine the forecasts and provide more accurate insights. By continuously leveraging from new data. AI enhanced exponential smoothing enables universities to make data driven decisions, optimize resource planning, and respond proactively to evolving educational needs. How to incorporate cyclical patterns into forecasting models? Let's look into this with one example in stock market forecasting. Incorporating cyclical patterns into stock market forecasting using artificial intelligence involves leveraging advanced machine learning techniques to identify and predict recurring fluctuations in stock prices. Cyclical patterns in the stock market are influenced by various factors, including economic cycles, market sentiment, and broader financial trends. The AI models such as long short-term memory or LSTM, network and support vector machines SVMs, can analyze historical stock data to detect these cyclical patterns by recognizing repetitive sequences and correlation that may not be immediately apparent to human analysts. These models can process large volumes of data, including historical prices, trading volumes, and external economic indicators, to forecast future prices and movements based on the identified cycles. By continuously learning from the new data, AI models can adapt to changing market conditions and improve the accuracy of their predictions. This integration of AI enhances the ability to anticipate market fluctuations, providing investors and traders with valuable insights to making informed decisions. The methods to evaluate performance of cyclical forecastings are also MAE, RMSE, and MAPE. Uh, in If I expand on my previous example, the artificial intelligence can incorporate additional data sources such as news sentiment analysis and social media trends to further refine stock market forecasts by applying all of these that we have earlier discussed in a little bit more depth. So I suggest you to look at these MAE, RMSE, and MAPE or MAPE in a little bit more depth for your learning using the university library system. The trend-based time series, identifying trends in stock market data, moving averages, linear regression, polynomial regression are few of the areas you can also explore and conduct research, learn differences between trends and other components like seasonal and cyclical. So by analyzing the sentiment of new articles, social media posts, and other relevant data, AI models can capture the impact of public perception and market sentiment on stock prices by looking at the differences between seasonal and cyclical trends. The characteristics of trend-based time series can be upward, downward, linear, non-linear. So it can be if the stock is going up or down or is not trading today or is having irregular movements in terms of non-linear trends. And any stock market data, you can look at Yahoo Finance or any other finances in terms of Coinbase or token market, or look at tokenomics for Bitcoin, Ethereum, and all that jazz. They all run in the similar fashion. Detrending time series techniques for removing trends from the time series data is called detrending. Importance of detrending in time series analysis. We'll discuss that using an example of detrending in stock market data. Here you go. Detrending time series data in the stock market involves removing the underlying trend component to focus on the cyclical, seasonal, or residual variations. AI can automate and enhance this process by employing machine learning algorithms to identify and eliminate trends more accurately. Techniques such as moving averages, linear regression, and differences between the integrated and into AI models to detrend stock prices data. For example, AI can use moving averages to smooth out short-term fluctuations and highlight the long-term trend, which can then be subtracted from the original data. Additionally, artificial intelligence can adaptively select the optimal detrending method based on the characteristics of the data, ensuring that the detrend series is stationary and suitable for further analysis. By incorporating artificial intelligence, the detrending process becomes more efficient and accurate, providing a clearer picture of the underlying patterns in stock market data and improving the reliability of the subsequent forecasts. Modeling trend time series ARIMA we have discussed earlier. Let's look into Holt-Winters because profit we also have discussed earlier. The Holt-Winters method is a powerful technique for forecasting time series data that exhibits both trends and seasonality at the same time, making it particularly useful in the stock market. For instance, consider a scenario where an investment firm wants to predict the monthly stock prices of a tech company. By integrating AI, the firm can automate the Holt-Winters method to dynamically adjust the smoothing parameters for the level, trend, and seasonal component based on real-time data. AI algorithms can analyze historical stock prices, trading volumes, and external economic indicators to optimize these parameters, ensuring that the model adapts to changing market conditions. Additionally, AI can incorporate sentiment analysis from news articles and social media to capture market sentiment, further enhancing the accuracy of the predictions. By continuously learning from new data. The AI enhanced Holt-Winters model can provide more reliable and accurate stock price forecasts, helping the investment firms make informed decisions and optimize their trading strategies. So, the incorporation of trends in forecasting, as we just discussed, using several trends and analysis. So, I'll not go into the details for how to incorporate trends into forecasting models, as I discussed earlier. Benefits of including trends components in stock market forecasting has also been discussed in terms of the Holt-Winters method in specific and the seasonal and cyclical trends. Evaluating trend-based forecasting models, MAE, RMSE, and MAPE, we can actually do the same thing on our Holt-Winters method as well. So I suggest you to conduct a little research on your own, that how would you apply the Holt-Winters method by looking at MAE, RMSE, and MAPE. This has been the third slide that came back just to remind you how significant are these methods in forecasting models. Seasonal time series, importance of identifying seasonality in stock market data, difference between seasonality and other components, trend and cyclical. We have discussed this in quite depth, so I'll skip and I'll go to the next slide. Let's look into characteristics of seasonal time series. The key characteristics of seasonal time series, such as regular, repeating patterns, fixed frequency, and the examples are seasonal patterns in stock market data like quarterly earning reports and holiday effects. So they have significant impact when we are investing or when we are trading. It can be everyday trading, it can be options trading, it can be mutual funds trading, it can be bond trading, or it can be any other investing that we need to look at quarterly earnings reports in major, and also holiday effects certainly have a certain trend establishment for the traders or investors to look into very carefully to either exit or go long in terms of holding their trades. Identifying seasonality in time series data. Let's look into an example on seasonal decomposition, autocorrelation plots, and seasonal subseries plots with an example. Seasonal decomposition, autocorrelation plots, and seasonal subseries plots are essential tools in time series analysis, particularly in the stock market, and integrating AI can significantly enhance their effectiveness. Seasonal decomposition involves breaking down a time series into its trend, seasonal, and residual components, providing a clearer picture of the underlying patterns in stock prices. AI can automate this process by using algorithms like seasonal decomposition of time series, or also known as STL, to dynamically adjust the decomposition based on real-time data. This allows for more accurate identification of seasonal patterns, trends, and residuals, which are crucial for predicting stock price movements. For example, AI can analyze historical stock prices, trading volumes, and external economic indicators to decompose the time series and identify seasonal fluctuations that may not be immediately apparent by continuously learning from the new data. AI can adapt the decomposition models to changing market conditions, improving the accuracy of the stock prices forecasts. Autocorrelation plots, such as autocorrelation function, or also known as ACF, and partial autocorrelation function, or PACF, as discussed earlier, help identify the correlation between stock prices and different time lags, revealing seasonal patterns and trends. Obviously, AI can enhance all these measurements on a very, very faster plane. Deseasonalizing time series, techniques for removing seasonality from time series data. I suggest you to conduct a little bit of research on this using your resources in terms of Google Scholar, IEEE Explore, or the university library. Importance of deseasonalizing in time series analysis. It technically allows us to look into external factors such as news sentiment and economic indicators to refine the autocorrelation analysis and improve the accuracy for us to place a trade or invest. Modeling seasonal time series. Overview of models suitable for seasonal time series are SARIMA, exponential smoothing, or Prophet, as discussed earlier. Steps to build a model for seasonal time series data. We have just looked into the STL, or the seasonal decomposition of time series, that allows us to dynamically adjust the decomposition based on real-time data, and this allows for more accurate identifying in terms of identification of seasonal patterns and trends and residual components for us to make an insightful or informed decision on top of that. Incorporating seasonality in forecasting, we just have looked into by looking at sentiment analysis and the economic conditions. So the incorporation of seasonality, we just discussed, looked at the ACF and PACF, which is technically the autocorrelation function, ACF, and partial autocorrelation function, which is PACF, in quite depth. Evaluating seasonal forecasting models, I would suggest you to look into seasonal forecasting models incorporation in MAE, RMSE, and MAPE, which we have discussed in quite depth earlier. In other model evaluation, that model evaluation can interpret seasonal forecasting models also for us. Univariate time series, let's look into this with an example in a little bit more depth. Let us change the gears, and rather stock market or university system, let's look into some healthcare scare that we had previously in the year 2019 and 2020, that was COVID. Univariate time series analysis involves examining a single variable over time to identify patterns, trends, and forecast future values. Incorporating AI into this process can significantly enhance the accuracy and insights derived from the analysis. For example, consider the analysis of COVID-19 case data over time. Traditional time series method might struggle to capture the complex dynamics and sudden changes in the data, such as rapid increase in the cases during waves or impact of lockdowns and vaccinations. AI algorithms such as long short-term memory, or LSTM, network and Prophet models, which we discussed earlier, can analyze historical COVID-19 case data to identify intricate patterns and trends that may not be immediately apparent through conventional methods. By leveraging AI, analysts can predict future COVID-19 case trends more accurately, or any such pandemic or epidemic, taking into the account seasonal fluctuations, the impact of public health interventions, and other relevant factors. For instance, AI models can incorporate data on vaccination rates, mobility patterns, and public health policies to refine their predictions. So single variable temporal dependence is temporal technically changes with the time. The examples of your univariate time series in stock market is closing prices and trading volumes. Even though we were discussing COVID-19, however, if we apply the univariate time series, it is applicable in the stock market as well. The common univariate time series models are ARIMA, or autoregressive integrated moving averages. We have discussed that in quite depth, so I'm not going to go into details of SARIMA, exponential smoothing, and Prophet. And in exponential smoothing in specific, Fort Winters is one of the area. Why these are being repeated? Because every time we have changed the time series model. At this moment, we are discussing the univariate time series model. The steps to build univariate time series model: data collection and pre-processing, model selection, parameter tuning, and model training. Since we have been discussing artificial intelligence in quite depth, these are the standard methodologies and techniques for AI to work with any of these models by incorporating the time series data or time series models, specifically in this case univariate time series models. The techniques for model validation is train, test, split, and cross validation. I suggest you to look into train, test, split, and cross validation in your time. So this will allow you to figure out how the cross validation is, and train, test, split allows us to look into the univariate time series models on stock market, COVID-19, university management system, or sales of a store. It can be Amazon, it can be Walmart, or something else. Forecasting with univariate models. How to use univariate time series models for forecasting. I just discussed with you the COVID-19. The benefits and limitations of univariate forecastings. Let's look into this with one example. Univariate forecasting in the stock market focuses on predicting future stock prices based on historical price data alone. This approach benefits from simplicity and ease of implementation as it requires only a single data series. However, its primary limitation is the ignorance of external factors such as economic indicators, market sentiment, and geopolitical events, which can significantly influence stock prices. Additionally, univariate models may struggle to capture complex nonlinear relationships and sudden market shifts, leading to less accurate predictions in volatile markets. So now let's look into the expansion of univariate to multivariate time series with one simple example. Multivariate time series forecasting in the stock market incorporates multiple variables to predict future stock prices, providing a more comprehensive analysis. By integrating AI, this approach can capture complex interactions between various factors such as economic indicators, market sentiment, and historical price data. AI models like LSTM, as discussed earlier, technically that LSTM is a network, and random forests can identify intricate patterns and dependencies, leading to more accurate and robust predictions. However, the complexity and computational requirements of multivariate models can be challenging, and the reliance on multiple data sources may introduce noise and require careful data processing. So we also use vector autoregression, or VAR, recurrent neural networks, technically LSTM layers, and deep learning models can also be applied on this area. Building multivariate time series, I suggest you strongly to look into this using the library resources, Google Scholar, or IEEE Explorer at the data collection and pre-processing to establish multivariate time series models by incorporating the artificial intelligence. And that's where you can use RNN or VAR, where you can do parameter tuning and model training using the trained data. If you have 100 data sets, that means you can use 20% in terms of the training model and check on next 20%, and the last 60% would be your actual data to apply the model after verification and evaluating the model in specific. Feature engineering for multivariate models. The importance of feature engineering in multivariate time series is significant, as we discussed in the LSTM and the other forecasting techniques. The techniques for the creating additional features such as moving averages, RSI, sales volume can also be looked into stock market. Incorporating external factors as discussed earlier in terms of social media sentiment and weather forecasts are also play the role in stock market as well. Feature engineering for multivariate models in the stock market forecasting. We can create additional features from price history. Examples are performance indicators such as moving averages, the RSI, and sales volume. We can also include features from other sources, for example, social media sentiment as discussed earlier, weather forecasts, etc. Multivariate models that have additional relevant information available have a chance to outperform univariate models in this case. The conclusion goes like this: time series analysis plays a crucial role in the stock market by providing a structured approach to understanding and predicting stock prices over time. By examining historical data, investors can identify trends, seasonality, and cyclical patterns that influence stock performance. Techniques such as moving averages, autoregressive integrated moving averages or ARIMA models, and more advanced machine learning algorithms in forecasting future prices and managing risks. This analytical method enables traders and analysts to make informed decisions, optimize trading strategies, and potentially maximize returns. It is essential to complement time series analysis with other financial indicators and market insights for a comprehensive investment strategy. Hopefully, this has given you some insights in learning the time series application by incorporating artificial intelligence and working within the on the prem or on premises or in the cloud by looking at all the feature extraction extrapolation for a trader or an investor or a university system decision maker or a healthcare provider to make insightful and informed decisions. Happy learning.